Hello everyone. The title of today's lecture is Types of Relations. So, as we have already covered what is a relation, now we are interested in determining what are its possible types. So, if we look now to the outline of today's lecture, here you can see that there are 5 different types of possible relations which we are going to understand. The first starting from reflexive, symmetric, antisymmetric, transitive, and finally what is an identity relation. In addition to these relations, like after completing all these relations, we will try to understand this important relation which will often come into the picture is called an equivalence relation. One more important relation which is an inverse relation. And to understand all these types, again there are some prerequisites, which that is some prior knowledge, that is we should already know something, and what is required today is that what is a relation. So if you are watching this video for the very first time, so do watch the first this video, that what is a relation, and then watch this video in order to get a good clarity. And also today's video might be a bit long, so do watch the video till the end in order to get a clarity on all the possible types of relation. So let's start with today's lecture. So let's try to understand what is a reflexive relation. We have already learned that a relation from a set A to a set B is a subset of the Cartesian product. We have already learned that a relation, which we often denote by this symbol R, is a subset of this Cartesian product A cross B. That is when we were defining the relation from set A to a set B. That while understanding the relations, there were two non-empty sets A and B. In today's lecture, we are defining the relations from set A to itself. That is, this R is today is a subset from set A to itself. So it will be a subset of A cross A. That is, this B is a set A itself. Fine. The second set is also A. Now, when we are going to call this relation R reflexive, then we are going to call this relation R reflexive if you collect all these ordered pairs A comma A, and they are in this capital R, for every member A belongs to this set capital A. Fine. Now here, if you see what this and this means, if I write in a shorthand, I can write it like this also, A R A. This means itself. That is, this element is related to itself, and now this property should be true for every element small a belongs to this set capital A. This property should hold for every element, right? So if such a thing happens, then we say that this R is a reflexive relation. What kind of relation it is? Reflexive. Let's take an example to get a more clarity on this. So the example which I am choosing now, suppose we are given a relation, suppose we are given a set A consisting of these three elements 1, 2 and 3, and we are given the relation R, and suppose it has some ordered pairs. So if I say 1, 1, 1, 3, 2, 3, suppose these three ordered pairs we have in the relation R. Now if you observe here, this property said that A comma A belongs to this relation for every choice of A. What are the possible choices of A? These are the possible choices we have. So we can now rub this to get some space. So how we have understood the relation when it is a reflexive, that is R is reflexive if and only if this ordered pair A comma A belongs to this R for every choice of A in the set capital A. So this property is very important. If you now see here that the choices of A which we have are A can be 1, 2 and 3. So what are the possible choices here? The ordered pair will be, in order for this R to be reflexive, 1 comma 1, 2 comma 2 and 3 comma 3, they all should belongs to this R in order for R to be reflexive. But you see here, only this ordered pair belongs and the remaining 2 does not belongs to this R. So we can say, since you can just take anyone, suppose since this 2 comma 2 does not belongs to this relation R, here R is this relation and this ordered pair is not present there, so we can say that this, therefore this R is not reflexive. Fine, this R is not reflexive. Now if suppose our R was such that it had more ordered pairs, now if I redefine my R, if my R was such like 1 1, 2 2, 3 3, 1 3 and 2 3, suppose this was my R, then in this case if you see now whether this holds or not, A comma A, try to pause the video and try to find it yourself. Yes, they of course belong, because you see this component 1 comma 1, 2 comma 2, 3 comma 3, they all are there, these three. So this property satisfy, and in this particular case we would have said that this relation R is reflexive. So a relation R is reflexive if this holds. That is yes. For every, of course, for every element A in the set. So let's now try to understand what is the second outline of the relation was a symmetric relation. So what is the symmetric relation? Symmetric. If you see the word here, there is something important which you can identify. What is this? It's something related to symmetry. That is what it says. What is the definition? A relation R. A relation R is said to be symmetric if and only if whenever this element A comma B belongs to this relation, this should imply that this B comma A should also belongs to R for my A comma B coming from this set capital A. Fine. So what is the definition? When a relation is said to be symmetric whenever this component is belonging, then this should also belong to the relation. It should not hold that if this is belonging and this is not belonging to the relation. So in that case we will say that the relation R is not symmetric. Let's again try to understand this type with an example. Suppose you choose your A to B. Let me choose here. Suppose you choose your A to B, the same set which we defined 1, 2 and 3. Now you choose your R to be a set. First I want to make you understand that it is not symmetric. So suppose my R has some ordered pairs 1 1, 1 2, 2 3 and suppose say 3 3. These are there. This is my capital R. Now if you observe here, you have to satisfy this condition. Now you have to first identify what are A and B. So if you observe here, they are different elements. They are not same. A and B are different. So what are different possibilities? These two are different ordered pairs which you have in your relation. Now choose the first one, 1 2. Now since 1 comma 2 belongs to this relation R, now for this R to be symmetric, what the definition says that B comma A is opposite, that is this 2 comma 1 should also belong to this relation R. But if you see here, 2 comma 1 is not present. 2 comma 1 does not belong to R. So that's why now from here we can say this relation R again is not symmetric. You don't need to check further when even if you find one element which is not present there, which does not satisfy this condition. So you don't need to move ahead whether if, like you can see also here, if now 2 comma 3 also belong to the relation but 3 comma 2 does not belong to the relation. So again if you have chosen that ordered pair, so in that case also you would have pointed out that this relation R is not symmetric. But this one is sufficient. Just for to make a clarity, this is sufficient. If one ordered pair is not belonging to, you can quote that also. Fine. Now if we can extend this relation. If this relation was like that instead of this, our relation R was like that. That if our suppose it was like this. Suppose this was my R. If you see now A and B, the different elements, that is A is not same as B, these are different. So what are the possible choices which you can have? 1, 2, so 2, 1 was there. For the same, you don't need to check, because if you see 1, 1, if I choose this my A, this my B, then the symmetricity does not make any sense here, because the B, A is also same. So you cannot repeat a ordered pair when you are collecting in a set. It will count it once. So that's why you have to check for those ordered pair which are different. So here the different one was 1, 2, and of course 2, 1 was there. So that's why this relation R qualifies in order for called to be a symmetric relation. Now let's try to understand what is an antisymmetric relation. So as the name suggests, antisymmetric. If now we try to think ourselves, the first keyword anti, that is, it is saying that the symmetry should, that the symmetricity, that part of symmetry should lose in the definition. That is, it should not hold what was happening in the case when we were discussing a symmetric relation. So how this is defined, the relation R is said to be antisymmetric. Now try to observe this. If and only if whenever this ordered pair A, B belongs to this R and B, A, they both belongs to R, then this two information should imply that they both are same actually. These two are equal. If these two are not equal, then what will happen? Try to pause the video and try to think it yourself. Now, what is the question, that if these two are not equal, what will happen? If A is not equal to B, then if this condition will hold, then what will happen? If you see, then you are satisfying the condition for it to be symmetric. But what we want? Antisymmetric. So that's why what we are saying, that these two should be equal, so that the symmetry should not hold. Fine. Like we can understand it one more way also, that if A and B are related to each other and B and A are also related to each other, then either they are same or they both cannot be related to each other simultaneously. That is, only one of the ordered pairs should belong to the relation R, but not the both. That is, I can rewrite it like this also. The second way, if my A is not equals to B, then either A may be related to B or B related to A, but not both. We want this should not, but not both. That is, they both cannot be related to each other simultaneously. Fine. So that's why we want it. We want it because the relation which you want to build is kind of an anti-symmetric relation. They are not symmetric. So they both ordered pairs cannot come into the relation simultaneously. So that's the reason. You can take an example again. Suppose I choose my A now to be x, y, z, and this R x y z x. If you see here, if you call this A, if you call this B, then B comma A is not present here. Fine. And if likewise in this case also, this relation R qualifies to be an antisymmetric relation because these two ordered pair does not belongs to the relation simultaneously. This we can understand. Now let's move ahead to understand the most important, one of the most important relation, transitive relation. Again, a relation R defined on set A is said to be transitive. I am writing directly. R is said to be transitive. If and only if whenever this A comma B belongs to this relation R and B comma C belongs to this relation R, then this should imply that my A comma C also belongs to this relation R. What it says basically, there are three elements now, that is these three are there in this capital A. Fine, all these three belongs to this set capital A. Or I can rewrite it like, if my set A consists of these three elements A, B and C, then if my first element A is related to the second element B, because the ordered pair is belonging in the relation R, so it means that they both are related. The element B is related with the C, then it is saying that the first A is also should be related with the last one. They both should be related. That is, this ordered pair should also belong to this relation R in order for R to qualify or R to be called as a transitive relation. So let's take an example to get more clarity. Suppose my A, choose some different A now. 1, 3, 9. Suppose this is your A. And let's me choose a relation R. 1, 1, 1, 3, 3, 9, 1, 9. Fine, this is your R. Now if you see, pick the ordered pair which are different in order to check the condition. So this is same, so you don't need to check. 1, 3 is there. 1, 3. So you left with B and you have to again check with some same starting with the same B. So you left 1, 3. So B is 3. This is your B here. So this is your B again here. So you find this is your A comma B, this is your B comma C. These two ordered pairs you got these two ordered pairs. Now you have to check whether A is related to C or not. That is, 1 is related to 9 or not. That is the ordered pair rather. Now the question is whether 1, 9 belongs to R. You can see it here. 1, 9. 1, 9. Yes, it is here. It is present here. So yes, the answer is yes, because it is here. So we can say that this relation R is transitive. So before understanding identity relation, I want to introduce what is called an equivalence relation, because we have understood the conditions required for it. Definition: So a relation R defined as some set A is said to be equivalence if it satisfies all these three types. That is, it is reflexive, it is symmetric, it is transitive. If a relation R satisfies all these properties, then we say that relation R is an equivalence relation. Right? Now let's try to understand this relation, identity relation. The word, this first keyword, identity, if you try to absorb this one, what it says basically that all the elements should be related to itself only, what it wants in order for this first keyword to be satisfied. Now let me write the definition, formal definition. There is some standard notation again in order to define an identity relation. This, suppose I am calling it by A, and again that set A is same on which this relation is defined. So now I am writing it like this: I defined on A, this called identity relation. If in this relation we have only these ordered pairs. What it means, what kind of ordered pair these are, in which all elements are related to itself only. Fine? So this is the kind of intuition and this is the definition of an identity relation. So we have understood almost all the major types of relation. Now there remains only one important relation. It is not a kind of a type, but it is a relation which you want to understand, an inverse relation. Let me know. Listen, we try to understand the last relation. Inverse relation. Inverse relation. Now if you recall, when we started defining a relation R, in the very starting, in the previous lecture, it was defined from a set A to a set B. Our relation R was defined from set A to a set B. There were two sets in the picture. So this R was from set A to set B. Now I am interested in defining one more relation, which is called as an inverse relation of the original relation R, in reference to this relation R. And now this will be defined from here to here, from B to A. The roles will change now. Now I am interested in defining relation from here to here. So how you can define this relation? If this R was collection of all these AB, such that this A was here and this B was here. This is how your capital R was defined. So now with the help of these ordered pairs, you will be able to define this R inverse. It will be collection of all those BA, reverse all the ordered pairs, such that in reference, like from where you are able to reverse, you are choosing, because they are there, this A and B belongs to this R. So with the help of all these ordered pairs, you are defining these ordered pairs and collecting all these ordered pairs, this collection giving a name R inverse, which is a relation now from B to A. Why it is from B to A? Observe now, because this B's was belong to this set, and this your A was from this set capital A. So here we are calling a relation R from set A to set B because the first elements A was from the set A and the second element was from set B. Now the roles have changed, so that's why we are calling an inverse or the original relation. We have understood what is the types of relation, what is an equivalence relation, and what is the most important, an inverse relation. So we have built enough motivation required to go further into the chapter and to the most fundamental concepts of function. So in the coming video, we'll be discussing the basic motivation required for what is a function. So do like our video and do share about our initiative among your friends. And do subscribe the channel. Thank you so much.